Okay, gang, here is our lecture for projectile motion that you guys should be watching Thursday, or before you come to class on Thursday. We're going to start with a story of back when I was at UC San Diego. I don't know if you guys are familiar with the colleges down at UC San Diego, but I used to stay in Muir College, which was a 10-story, and dorms at Muir College was a 10-story high-rise that overlooked the beaches of La Jolla, California, which I think back and I realize that I will never ever have that kind of an ocean view ever again, or ever live in that proximity to such beauty for the rest of my life, because that's really a high-rent district in that part of the world. But my buddy had to live in Ravel, and Ravel had these things called the mud huts. And the mud huts were these, they looked like earthen brick, funky apartment things that kind of looked like beehives in a weird kind of way. And, but like mud bees. It was just, they're just ugly places. And what we would do is, because we were often bored and and we wanted to get to the attention of some of the ladies at college, although ladies at Ravel College, well, let's just say that I was doing pretty well over at Muir when it came to pickings, but of course, at the same time, I was also a king nerd, and so I was not having a whole lot of success down there. And so what we would do, one of these stupid things that we would do to try to gain the attention of the girls, would be to launch water balloons at them, because, yes, even though you go to college, there's still a pretty juvenile thing to do. However, we would do it in, of course, the way that physics majors would do it, which is the hard way. And so we had these dorms, and the dorms were about 3 stories tall. And those were the ladies that we were trying to impress. And we would launch water balloons from one side, and we know that there would be this initial velocity. We would launch it with a certain speed, and we would try to get it to clear. Okay, and there would be at an angle, and we would try and get it to clear the apartment building and land on the ladies having lunch on the other side. Yes, not exactly the best way to get positive attention, but at least we would be noticed. And we thought, hey, that's all it took. So the way it would work is that there was a hallway down the middle of the dorm, and we would have somebody in one side of the dorm that would be able to run through and check to see whether the balloon was too far or not far enough. And we can only pull the surgical cord for the slingshot so far. So we were just adjusting the angle. And so he'd run through, and if it was too far, then it would be, not enough angle, that we need more angle up, and if it was too short, then it was too high, so we'd need to angle it out a little further. And we had a great time until one day we actually shot one into the mirror, not into the mirror, into the window of the apartment. And our buddy that was in there got absolutely doused, because the windows were covered with a industrial strength screen, so that people would really have to work to jump out of them. Yes, it was an issue. It's an issue when you go to high-powered schools. However, when you launch a balloon into a window with that kind of velocity and it hits the screen, the water, it doesn't vaporize, but it splatters into billions and billions of water droplets, and it just doused the entire room, including our buddy that was inside. And so, luckily, that was not my dorm room, but it was funny to watch when we did see it. Okay. However, we do know that this is... Oh, and while we're launching it, the water balloon, when it was launched, that would be called a projectile. And the projectile is the object that is going through the air. And when an object is going through the air with the only thing acting upon it is the acceleration due to gravity, then it follows what's called a trajectory. And usually our trajectory when we are launching a projectile is a parabola. It is given to us by a quadratic equation, which you guys may have seen in our kinematic equations. Okay, now, at any given moment, now we know that we can accomplish this. We can accomplish this if we have the right angle, because we know that this right here is our, this is the acceleration that it's experiencing, and this acceleration is equal to negative 9.8 meters per second squared j hat. Okay, and so if we draw a little axis in here, okay, we can start analyzing what we've got, analyzing our water balloon path. Okay, and so if we write our components, or write our equations, and the way we analyze this, is we write our components with their own kinematic equations. We separate the kinematic equations for each component. Okay, and so the first one, our Vx, is going to equal V naught x plus AT. So whatever our initial horizontal velocity is, okay, plus the acceleration in the x direction times time. But what is our acceleration in the x direction? Well, that goes to 0, right? And so that leaves us with Vx equals V naught x, which means that our initial velocity is constant. Okay, not our initial velocity, our horizontal velocity is constant when we have a trajectory. That so long as we're in the air, our horizontal velocity is not changing. There's nothing acting on that horizontal velocity. Okay, and so all of those, the horizontal velocities are all the same, and they all keep going in the same direction. Okay, we go to our next kinematic equation. We have x equals, or our displacement equals V naught, equals Vx plus V naught x over 2 times t. Okay, but we know that our velocity is constant, and so Vx equals V naught x, and so that gives us a little 2V naught x, and that's going to cancel with the 2, giving us just V naught x times time. And this is a very common equation that we will be using in our trajectory motion, particularly when we're dealing in the direction that does not have an acceleration acting on it. Our displacement is just our velocity times the time. Okay, then our next one is, there's the quadratic that we were talking about, and that actually shows the displacement, or shows the displacement at any particular time along our path. And delta x equals V naught x times time plus 1/2 AT squared. But, as in the previous problem, our acceleration in the x direction is 0. So that makes that term go to 0, and we're left with that same delta x equals V naught xt. Similarly, on the last one, the v squared equals V naught squared plus 2a delta x, our acceleration again is 0, which leaves us with Vx squared equals V naught x squared, and that's a pretty trivial solution for that. Okay, so those are the kinematic equations for the x direction, and you'll see that we really only have the one that we have to worry about, the delta x equals V naught x times time. But now we have the y direction. And so we have Vy, or velocity in the y direction, equals V naught y plus a yt, except this time we actually do have an acceleration that we need to concern ourselves with. Okay, we're also going to have our average velocity, which is going to be the velocity at a given time plus our initial y velocity. But if you take a look at that, then our initial velocity over here is going up, but because we have an acceleration, our velocity is actually going to be decreasing each step we take. We go through up until the very top. I couldn't draw that arrow any smaller without it still showing that it was going up. That should actually be 0 at the very top of the parabola, where our velocity at that moment is 0. And then we start decreasing, okay, decreasing our velocity, in other words, making it more negative as we fall back down, to the point where if we land at the same place that we start, then our velocity in the y direction is equal to our speed in the up direction is equal to our speed in the down direction on the way back, because it is a symmetrical parabola. And we'll get to that in a little bit. Okay. There's the other kinematic equation. This also shows our quadratic equation, where delta y equals v naught yt plus a yt squared. And this one we will also use significantly more. Okay, and ay is sometimes written as g. Okay, and remember the g is the same thing as the a over here. This g, this value is the same thing as this one over here. That's this negative 9.8 meters per second. I'm going to write it this way sometimes, just to remind you guys that an acceleration is really that we are changing our speed by 9.8 meters per second every second. So every second that we are under the acceleration due to gravity, our velocity is changing by 9.8 meters per second in the negative j hat direction. Okay. Then we come to our last one, where Vy, let's back up there. Where Vy squared equals V naught y squared plus 2ay delta y. And that's how we can figure out our, that's that fourth kinematic equation in terms of y. So we have our x direction kinematics and we have our y direction kinematics, and the trick is they don't cross over. There is one way that they are linked. Okay, and we do all of our problems separately, keeping them linked with time t. That time t is the only thing that the two sides really have in common. And you will use that to go back and forth. You'll use that time to go back and forth to help solve both sides of the equation. Okay, which brings us to when we're actually launching something. So let's say we launch something at an angle. We have our initial velocity, and we have that theta. Well, this theta is called the launch angle, and it is the angle above the horizontal that we're launching our projectile. But this just leads to our v naught in the x direction equals v naught cosine theta, and v naught in the y direction equals v naught sine theta. And so we're just going to have that off to the side for right now. Okay, so let's imagine we're launching something, and it's going to have this trajectory like a parabola. Now there are a couple of tricks to the trade. This right here is the line of symmetry of our parabola, and it so happens that so our graph is symmetrical, that our time up to this point equals our time down. So you may find it useful to find the time it takes to get to the top, or the time it takes for it to get from the top to the bottom, and then that will equal the time to the other side. So let's say we have our v naught y going in the up direction, okay, and to find out where this halfway point is, it would be where v naught y equals 0. And with that amount of time, then we could find out how far, that's half of the range that our thing might travel. So that's, if we're shooting from a base level to another, to the same level, that's going to help us a lot. That creates our symmetrical graph. The other thing is that at this point, our delta y also equals 0. So if we do land at the same level that we start, our displacement, our delta y displacement actually is 0. And that helps us go back to our other equations and help solve some stuff out of there. This truly simplifies the problems quite a bit. Okay, and those are the values for our velocity up at the top, that our value for x doesn't ever change, and our value for y at the very top of the arc equals 0. And so, and that really concludes how we handle our projectile problems. But by popular demand, I have been asked to do a sample problem. So we're going to do that right now. This happens to be number 11 on page 102. And it reads, in a local bar, a customer slides an empty beer mug down the counter for a refill. The bartender is momentarily distracted and does not see the mug, which slides off the counter and strikes the floor 1.4 meters from the base of the counter. If the height of the counter is 0.860 meters, A, with what velocity did the mug leave the counter? And B, what was the direction of the mug's velocity just before it hit the floor? So let's draw this situation. We have a bar with a mug. Okay, so there's our mug. And the bartender does not see the mug slide. And so it's got this velocity heading off the counter. And the height of the counter is 0.860 meters. And the trajectory it takes to the floor of the bar gives us a distance away from the bar of 1.40 meters. So, we are given what? We are given that its displacement from the counter is 1.40 meters. Okay. We are also given that its delta y equals a negative 0.860 meters. And we also know that our acceleration in the y direction is going to equal negative 9.8 meters per second squared j hat. And let's fix these. This is going to be j hat and that's going to be I hat. So those are the things that we are given. Now we know that there has to be an initial velocity, and that initial velocity, by the way, will be in the x direction, right? Okay, and for this case, and I don't know why I did it in this direction, but I always draw my diagrams right to left. We're going to take x in the leftward direction to be positive just for simplicity's sake, because there's no reason for that to change. Okay, so A, it says, with what velocity did the mug leave the counter? Well, we've got two things. A, find velocity. Find the velocity at which we left the counter. Well, how are we going to do that? We need to solve two things. We need to find out how long, the amount of time it took for our mug to hit the ground, and then transfer that back over to how far it traveled for the x direction. So we're going to use the y, we're going to tackle the y first. Y direction. Yeah, I don't need to write that. We're going to tackle y first. So, what do we have? We have displacement, we have acceleration, we need time, and we have, oh yes, we also have, let's write that in here, we have V naught y, we know that equals 0. So that is information we do have because it's a horizontal bar. So, we are going to use delta x equals, I'm sorry, not delta x, delta y equals 1/2 at squared, because we know that, let's go back and write the whole thing here. So it's going to be v naught y t plus 1/2 at squared, but we know that this is 0 because v naught y equals 0. So we're left with delta y equals 1/2 at squared, or our time equals the square root of 2 delta y over a. And that winds up being 2 times, and what was our change in height? 0.860 meters over 9.8 meters per second squared. And actually, that's negative and that's negative, which allows us to cancel that out to be a positive. And it turns out that our time is going to equal 0.41419 seconds. So this is what our time that we're going to fall equals. Well, now, if we have that amount of time, we can find, if that's how long it took, so delta x equals v naught x times time, or we can solve this so that v naught x equals delta x over delta x over our time that we had. And so delta x is going to equal, sorry, not delta x. We don't want delta x. We want v naught x, which happens to be our initial velocity, is going to equal our 1.40 meters divided by our 0.419 seconds, and that equals 3.34 meters per second. That is our v naught x. Okay, which brings us to part B. And part B asks, what was the direction of the mug's velocity just before it hits the floor? Well, let's go to our next. Let's replicate this and let's do part B. B is essentially find theta with the floor. So we want to find that theta right there. Alright, well, what's that going to be? That is going to be our theta is going to equal arctan of, well, what do we have? It's going to be arctan of Vy over Vx. Okay, so our angle with that over the floor, well, what's going to be our Vy? Well, we know that our Vy is going to equal, from our kinematic equations earlier, Ayt. Okay, and we know that V naught was 0 because it was launched horizontally. And so that's going to be negative 9.8 meters per second squared times our 0.419 seconds. And that gives us 4.11 meters per second, and that would be negative. Okay, and then we also know that Vx, well, Vx is the same velocity, and that's going to equal what we had on the previous screen, which was 3.34 meters per second. So our theta is going to equal arctan of negative 4.11 meters per second and 3.34 meters per second. And that winds up being a theta equal to 50.9 degrees above the horizontal. So that's number 11. That's how you work these things out, and hopefully you notice that we go back and forth between x and y's using time as our linkage, and luckily some things canceled out and other things didn't, and you'll find that this happens a lot, that there's a lot of zeros involved, and those will cancel each other out. So that's it for this one, and hopefully this is enough to get you guys started and get you guys to the next couple assignments. We'll see you guys on Monday.